Thank you. So the talk is slightly different than what appeared on the abstract. So I'm going to speak about Min+Convolution, three sums, and Additive Combinatorics. This is joint work with Timothy Chan, who's sitting here. So the previous two talks also mentioned quite a bit about three-sum, and it's going to be slightly different, and so the whole workshop is going to be about how different problems are hard because of threesome, and I'd like to take the other approach, see if we can maybe show something algorithmic. So I'm going to take a look at problems which I call SumSet problems, and threesome is exactly such a problem. And in threesome, as you've seen the definition this morning, and you'll see it probably several times further in this workshop, you're asked whether you have you have sets A, B, and C, and you'd like to know if you have an element from each such that A plus B equals C. Another way of writing this, an equivalent way, is asking is the set A plus B intersection C equal to, is it an empty set or not? In other words, A plus B, you're looking at it as the Cartesian addition, so you're looking at it whether when you take a look at all the addition of all the elements of A and B. Okay? So what do we know about threesome? We know everything that was already mentioned this morning. So we know that it's according to Seth, a problem which you go to work and you get accepted according to this problem if you can solve it in n squared time. We know that for integers that Bar-Ilan, Domain, and Petrashku actually shaved off a log squared factor, and for real values we have the result of Gruland and Petty from a couple of years ago, where they shave off a log factor. And in general, a lot of problems in this workshop, we're going to take a look at what is called threesome hardness, and there are subquadratic reductions from threesome. And one of the types of reductions which we use are called truly subquadratic, and this means that you really want to shave off a polynomial factor. So you want the reductions to be into the 2 minus epsilon, otherwise they don't have, they're meaningless in the sense of polynomial time. And this has probably been mentioned, it's going to be mentioned several times. There have been a bunch of geometric reductions starting from the time of Gaggentin and Overmars in 1995, and then Michal Petrashku with his, what was mentioned in the previous talks, actually sort of used convolution threesome to actually give it a little bit more structure to the reductions. The previous reductions were more of a geometric flavor. So this is what we know about threesome, or at least this is what is in the sense of what this workshop would say. And I want to take a look at a different problem, which is also a very important problem, is the min-plus matrix multiplication problem. You're given A and B and two matrices, two n by n matrices, and you want to compute the matrix multiplication of these two. And the matrix multiplication is of a special form. You're not looking at the regular matrix multiplication, but you're looking at min and plus as operations. So you want to you just replace the regular multiplication by sum and the regular sum by a min. And the min plus matrix multiplication is an important problem. It's also known to be equivalent to the all pairs shortest reduction. You can reduce it in both ways, and a couple of years ago, Ryan Williams showed that you can actually solve this in n cubed divided by 2 to the order of square root log n. And another problem that I'm going to actually look at more today is the min-plus convolution problem, which is a similar problem to the min-plus matrix multiplication. And here it's a convolution problem. So you're given vectors u and v, and you want to compute the vector just like you would do a regular convolution, but instead of having, once again, this, you're just replacing the same operations as you did for the min-plus matrix multiplication. In other words, instead of you're replacing the multiplication with an addition, and you're replacing the addition with a min variant. And Michal But Rashko showed that you can actually reduce this to min plus matrix multiplication, and therefore it's an important special case, and it has been shown to have lots of applications on its own. Okay, so why do I call this a SumSet problem? Because you can take this problem, the min plus convolution problem, and you can actually define sets for u and v. You take your set. You can take a set AU where you just define your UI as a pair IUI, and you define the set B for the vector Vj, where you define a JVJ, and then you can notice that your YK, which you're trying to compute up here, is actually a minimum KZ, where you set the K and you're looking at a minimum Z, where it belongs to AU plus BV. Okay, so the K is what sums up to I plus J, and then you get a minimum on the Z. So it's also a SumSet problem. So you have these two problems which are sort of SumSet problems, and what we want to do is, what we took a look at was we looked at the math of these SumSet problems, and this leads us to a field in math called Additive Combinatorics. And so Additive Combinatorics is a relatively young field in combinatorics. It connects additive number theory and combinatorics, and it has relations to theoretical computer science. It's been used in computational complexity to show all kind of lower bounds, and it's also been used to show combinatorics of certain graph problems. But it has had, at least we don't know of any algorithmic applications that it has been used for. And in this talk, what I want to do is I want to show you how you can use additive combinatorics for some special cases of three-sum and min plus convolution, which are interesting special cases. Okay, so I want to show you the result actually with the specific problem that has been looked at, but I consider it more of a toy problem so that we can actually understand the result, how we use additive combinatorics. It's simpler to use it in this case, and then I'll sort of show you the little bit more interesting case. So here's a problem that was looked at. You're given, it's called three-sum in a preprocessed world. So you're given sets, some sets, A0, B0, and S0 as input which you need to preprocess. So each one is of size order of n. And you want to preprocess them, and then you get queries afterwards. And the queries are of the form, you're given a set A, B, and S, and these are subsets of your ground sets, A0, B0, and S0. And what you're asking is whether you're asking the regular three-sum question. Is A plus B plus S, is there an element from A plus an element from B, which is equal to an element from S? But you're asking this on basically on a subset of your ground set. So you can do pre-processing work, and the question is what you can do. If you pre-process, can you answer these queries in quicker than what you do for a regular three-sum problem? Okay, so this problem was looked at by Ryan Williams and Nikhil Bansal, and in a paper, it was among other problems, and they mentioned that what you can do is you can actually pre-process n in n to the 2 plus epsilon pre-processing time, and then afterwards you can actually answer queries in n squared times log n divided by log to the 5/4, and at the time at least this division by log to the 5/4 was a little bit better than what you could do than what was done with three-sum. So what I want to show you now is how you can actually solve this in pre-processing in O tilde of n squared time and actually answering the queries in order of n to the power of 13/7. Okay, and the way we're going to do it is we're going to use this result from additive combinatorics. So let me present to you the result. And the result is a result by Balog-Szemeredi-Gowers. And this theorem is, the way I'm going to state it is a little bit more generalized than the original formulation. But there's several formulations of this theorem, so this is one of them. So let's say you have three sets, A, B, and S, and they're sets of size n, and they're subsets of some abelian group. Now, if you get a subset G, now this subset G is a subset of the Cartesian product such that the sum of elements belongs to the third set S. Okay, so they're looking at this special G, which is a subset of the Cartesian product where the element sum belongs to the third set S. Okay? If you have this set and it's quite big, so it's of size at least beta to the n squared, where beta is some parameter which you can choose, then there must exist subsets of A and B, A prime of A and B prime of B, such that one, the Cartesian addition of these of A prime and B prime, it's actually not too big. But on the other hand, their Cartesian product of the elements here, intersection with that G, is actually really big. So to actually think of it, to understand this result, the combinatorics usually like to choose beta to be a constant. We're not going to do that, but they like to choose beta to be a constant, and in that sense, you get that the sum of A prime plus B prime is order of n, but the intersection would be order of at least n squared times some given some constants. So by us, we're going to choose beta to be a little bit more interesting. What they usually don't do, the combinatorics usually don't do, but in that sense, there's quite a big gap. So in other words, you're getting something which is small in the addition, in some sets, but the number of pairs which are from G and in this set is actually quite big. So that's the theorem, and I just want to point out that this theorem is not a constructive theorem. It's there are several proofs, and it's not constructive. So we actually we actually have a construction to actually construct these sets A prime and B prime, and it's a bit technical, and it's in the stock paper, which from the last talk, and it takes us randomized order of n squared time given log factors. And we do this by using a proof, by following one of the proofs, which is actually a randomized proof. So it takes a little bit of technical work, but it's not overly surprising. And the deterministic one is a little bit harder to achieve, and we achieve this. You can just take a look at the factors here, and we use rectangular matrix multiplication and sparse FFT solution to actually achieve this. So that's a little bit more interesting. So I really don't want to go into the construction, but I do have to mention, of course, that it's not, that the theorem itself is not constructive, but we do construct it and use it. So how do you use the theorem? So the first thing that we do is we take a theorem and we'll actually use it over and over again to obtain, to sort of peel off the elements. So what we really want to do is we take this set of G, which is this special subset, and we really want to cover G in some sense. We really want to cover it. And we do what you naturally do in computer science, is you use the theorem, you get an A1 and a B1, and then you extract the elements from G, and you do it again, and you do it again, and you do it again until you've covered almost all the elements. And you get this, by using this theorem over and over again, you get the properties of the theorem. So the sum of each of these sets is not going to be bigger than, it's the same bound that we have from the theorem. And once you've done it over and over and over again until you've had enough, then your leftover set is going to be small. So in other words, before it was at least beta of n squared. Once you're under this, then you can't use the theorem anymore, and you're stuck with a set which is smaller than beta of n squared. And the number of rounds that it's going to take in order to do this is going to be 1 over beta squared, because you get, every time you take over beta squared divided by n squared elements, and just keep on doing this until your set is empty. Okay, so the first thing we did in the paper was we sort of tightened this a bit, and we, instead of 1 over beta squared, by carefully making analysis as we went down with the peeling off the sets, since the sets became smaller and smaller, you can make a more careful analysis, and we actually could transform this into a 1 over beta instead of a 1 over beta squared. Okay, so now let me go back to, so this is the corollary we achieved, and I want to come back to the problem that we had here. So our problem was 3-sum in a preprocessed world. So you're given these sets A0, B0, and S0, each of size order of n, and you want to preprocess them, and then you get a query, and you want to know whether the 3-sum answers yes or no. So you just do the following. You just use what we're going to do is we're just going to use the theorem. So you take your sets A0, B0, and S0, and you just apply the theorem we just mentioned, the BSG theorem, the Balog-Szemeredi-Gowers theorem, and you get an A1, B1 till an AK, BK, and the R, which is the leftover, such that their union covers all the pairs which have sum in S of 0. Once you've done that, you get your query. I'll get back to the times in a moment. You get your query, and then what you just do is you go take a look at R, and you go over all the pairs A, B, and R, and you check if A plus B belongs to S. And then for each of the AI BIs, you first go and you compute A intersection AI, B intersection BI, which is really easy. And then you want to compute this A intersection AI and the B intersection BI, which has to be a subset of AI plus BI, and its size is promised to be by the theorem, the size of AI plus BI, its size is promised to be 1 over beta to the 5th of n. And then once you do that, for each of these elements in this set, you check if it belongs to S, and then you've actually checked everything. So how much time does this take? So for the initial thing, the BSG, we mentioned that we could do it in n squared time, and this is exactly what we do. We just use the BSG theorem, our construction of the BSG theorem. I'm speaking about the randomized solution here. And then afterwards, we go over all the pairs in R, but the R itself is not too big. It's beta of n squared, so that's easy enough. You compute this. This is just simply linear time. And then over here, I'm skipping this line for a moment because this is sort of the tricky line. But then for each one in this set, since this set is not too big, it's 1 over beta to the 5th of n, so we can check each one. That's not too much. I do mention that we're looping over AI, BI, but the AI, BI, we promise that there's only 1 over beta of them, so we're only going to hit 1 over beta times 1 over beta to the 5th n. And then we've got this line, which is a little bit more tricky, and I claim that we can do it in 1 over beta to the 5th. I'll get back to that in a moment. But putting this all together, you get beta of n squared time because of this line for the query, and 1 over beta to the 6th. As I mentioned, 1 over beta times around, and each one is 1 over beta to the 5th n. So you get 1 over beta to the 6th n. And if you put a trade-off of 1 over beta equals n to the 1/7, you sort of just get this n to the 13/7 time. Okay? So that's really the whole algorithm. We're using the Balog-Szemeredi-Gowers theorem, reiterating, and just carefully using it and sort of using it as a cover. So that really shows the power of this tool of additive combinatorics, where using the regular methods, Ryan Williams and Nikhil Bansal were using the regular methods, and it was hard for them to achieve something. Perhaps we can use algebraic techniques which can actually do a little bit better. Okay, so that's this problem. So I do have to mention that this was sort of the tricky part. How do we do this computation? And so we use a special FFT lemma, which says that if you're given if you're given A and B of size n, and you know that their SumSet is order of n, and then you're even given a target set, which A plus B is a subset of, and you know what it is, and it's of size order of n, then A plus B, you can actually compute it in expected order of n time, or deterministic a little bit more than that. And in our case, if you go back, we knew we could upper bound what the set was in. We knew we had a ground set T, so we can actually do this. Okay. Okay. And how do you do this? You do this by some kind of form of pseudo-additive hashing. I really sort of don't want to go into this very much, but it sort of follows along similar lines to what has been mentioned this morning. There's similar stuff. So that's also a little bit more technical. So let me go back to the special cases of three-sum and APSP, which we mentioned. So there's been quite a bit of work on special cases of three-sum and APSP. So one of them is when you have small integers. So there have been results by Alon, Galil, and Margalit already from the early 90s, and by Seidel, showing that if you're looking at an all-pair shortest path where all the weights are some given constant, then you can solve it with this constant, if it's an undirected graph with a constant to some constant factor and to the 2.373s, and if it's directed, you can do it in a little bit, it's a little bit worse, but you're assuming that all your weights are within 1 to c, integers within 1 to c. If you have small integer and you're using Min+Convolution, then you can actually also solve this, once again with this, if the elements are all in with from 1 to c, then you can actually also solve this in c times n log n by using an FFT. And also, if your three-sum is bounded by, in a world of numbers which are up to constant times n, also integers in constant times n, then you can also solve it in c n log n. So these are easy special cases which are known. Maybe easy is in quotes purposely. People worked on this a bit, especially the APSP problem. But let me show you just some open special cases. So the following problem: small difference integer Min+Convolution. So you're given two sequences AI and BI, and their differences. It's not that the values are some constant, but the differences between them are constant. So AI plus the difference between the consecutive AIs is bounded by a constant, and you want to compute their Min+Convolution. Or an equivalent problem is the bounded integer monotone convolution. So you're given some two monotone increasing sequences, and they're also bounded by this c times n, and that's an equivalent problem. Another equivalent problem is a problem from pattern matching indexing problem called binary jumbled indexing. And there you're given a string, and you want to compute for each I the number it's a binary string, so you want to compute you want to preprocess the string, and then you want to compute the minimum number of ones or the maximum number of ones of all strings of length, specifically I. And this has been posed this problem has been looked at by many people. There's maybe 20, 30 papers of people who looked at this problem, and all they could do was shave log factors off. There's a preprocessing and a query time, so it depends on what you do. But either way, the preprocessing time for anything natural was the shaving off of was you could shave off log factors, but not better than that. And this is. And another equivalent problem is the bounded integer connected monotone threesum, and when you have a 2D version, so you're looking at dots in the, you have a 2D problem and you want to connect the threesum problems, and your values are sort of organized in a 2D fashion. So this is also another equivalent problem. So all these new results, I want to show that all these new results can actually boil down and solved in we can actually do better than what was previously known, and we can actually come up with, instead of an n-squared solution, an n to the 1.859 or a deterministic 1.864. Okay, so I'm going to take a look at one of the problems. It's called bounded integer monotone Min+Convolution. So you're given A and you're given B, you're given two sequences, and you want to compute this C. That's just the regular Min+Convolution, and the monotonically increasing and bounded problem was that the AI plus 1 minus AI is greater than 0, and the BI, so the differences between them are increasing, but overall they're bounded by some constant times n. And I'm going to even simplify this further to just make it simpler, but the solution holds just the same. And I'm going to just actually show the differences are 0 or 1. Okay, so the solution is actually, it doesn't make much of a difference whether we use the previous formulation or this formulation. The solution that we'll show actually solves both, but it's a little bit easier to see this problem directly. Okay, so I want to view this geometrically. So I'm taking a look at the two sequences A and B, and the way I'm viewing them is I'm sort of laying out the sequence AI, and this is our 0, 1 to n, their values, and I want to view I'm viewing it in a 2D sense, and this is what I'm viewing, and I want to take a look at the SumSet of the problems A plus B. And when I say SumSet, I'm taking a look at when I take a point AII and BJJ, so their sum is AI plus BJ, I plus J. So when we take a look at this drawing is a little bit wrong, but it should be going like this and then sort of coming back to a point here. So that's my, I apologize for that. But we're getting this sort of amorphous shape, which is the sum of any value there plus the sum of a value here. Let me just explain to you why it looks like this. So this is our A plus B. Here we get our AI plus BJ, and there is our I plus J. And the reason it looks this way is, take a look at the upper envelope. It's monotonically increasing by at most 1, because if you have AI plus BJ and I plus J, then, well, you take a look at the next one in line, and the difference is only going to be 1, because we assume the difference is 0 or 1. So you're going to have, so basically every time you move forward a column, you've moved either by the I coordinate or the J coordinate. They can only move by 0 or 1. So it's increasing, so it has to be increasing, because as you move forward, it increases, but it's either, the change is either 0 or 1. The same is true for the lower envelope, and the interior is fully solid, also for the same reason. You take a point here, you take a point here. Both of them have, when they're on the line of k, then the second one, so the second, the y value is equal to k all along. And so as you move along, if you have this value and you move to the next value, the change is going to be -1, 0, or +1. And you just sort of, you start from this point and you're moving back and forth until you reach this point. So you basically have the whole interior fully solid. So that's how we view it geometrically. Now, our goal is to compute CK, which is the minimum of I plus J equals K, where AI plus BJ, of AI plus BJ, where I plus J equals K, which means that we're looking at this line. And we want to look at we're looking for the minimum value, which is exactly the value here. So in other words, we're looking for the upper envelope. That's what we're really looking for. So we want to compute, when we get these two lines, we get this full value, and what we really want to compute is the upper envelope of this sum value. Okay, so how can, so one way, of course, we can just do it is compute it directly in n squared time, but we want to do it better. So how can we do it in better than n squared time? So the idea would be to approximate the upper envelope. So in other words, I'm willing to sort of compute roughly where the upper envelope is, and then sort of check whether it really, each value, whether it belongs to the upper envelope or not. And how will we do this? So let's sort of view this geometrically. So what I'm going to do is I'm going to take A and B, and I'm going to partition the space into smaller, I'm going to round it down. In other words, I'll take this whole space and I'll just round down A and round down B, each one into n divided by r space. So each square is going to be r by r. And the way I'm going to just round it down is simply taking each value and just rounding it down by r. Okay, so we get a sort of this line and this one, and we round it down, so each one is sort of rounded down. Now, the number of points in each of these graphs is going to be n divided by r, because it was a linear line, and now since we've rounded down by r, it's going to be n divided by r points. And instead of a point ai plus bj in the sum, ai plus j, we get an ai plus bj divided by r, lower bounded, I plus j divided by r, but we do have to be a little bit careful. We might lose 1 in either of the coordinates because of the rounding, but we're not too worried about that. We can live with a small rounding error. So when we take a look at the result value, when we take the first one and we do a Cartesian sum of these two, we get a rough approximation, a Cartesian sum of the value of A plus B. And the upper envelope is also a Cartesian sum. Now, what's nice about this is that the time to compute it isn't that much anymore because we have n divided by r points here and we have n divided by r points here. So the time to compute this whole thing is n divided by r squared. And that's better because we have this divided by r. So what we're really looking for is we have this approximation, and now we want to look at the values and find them here. So as I said, the computation to compute this rough approximation, we can do it in brute force and n divided by r squared time. And get this upper envelope, which is also an approximation. It's also of order of n divided by r points. But the problem is we might be unlucky. It might be the case that all our n squared points ended up on the upper envelope or in the approximation of the upper envelope. So in other words, maybe they all collapsed into this narrow thing and they're all on the upper envelope. So where does one go from here? So we want to make an argument on this upper envelope. Well, either the upper envelope, it represents, there's not too much on the upper envelope. In other words, it represents few pairs, some sums, one from here and one from there, or it has some kind of special structure. Now this is exactly the Balog-Szemeredi-Gowers theorem, and we're going to use that. Okay, so in other words, the argument, I just want to make it clear again. So we have this sum, and maybe we cut off a big chunk of this red stuff and threw it out, and then we're lucky because we threw out almost everything, and then we have very little left over here on the yellow line, and we don't have too much to compute. And the other option is everything sort of shrank and fit into this thing, or almost everything, but then there's lots of nice structure, and we want to use it. Okay, so we're using this corollary which we had before, which is from the Balog-Szemeredi-Gowers theorem, and we're taking our S. Our S is the upper envelope points, these yellow points. And what we're going to do is we have this rounded down value, which we just denote by rounding it down divided by r. So in other words, we're taking the points from A and B, and if we have a point AII, we're rounding it down and rounding down the I as well, and the same with the B points. And then we get these pairs. These pairs are a point from A and a point from B. Which one? So we get this two pairs together, and then we're looking at the A plus B, and that's of interest if it's on our upper envelope. And if it's not on our upper envelope, then we're lucky. We don't have to check it. Okay, so and this is our S. So we have A, which is the original set A rounded down, B, the original set B rounded down, and S is the upper envelopes and after they're rounded down. Okay. So here's the algorithm under this, using this idea. So we take A and B, and we round it down to, and we round both of them down to these r by r squares. And then we compute on the rounded down A and the rounded down B, we compute their Cartesian sum and do this brute force and take the upper envelope of the rounded down version. And then we use the Balog-Szemeredi-Gowers theorem on these three sets. So the rounded down A, the rounded down B, and the sum that we get from the rounded down upper envelope. And we use the corollary, in other words, we get A1, B1, A2, B2, A3, B3, all the way up so that we get a cover of the pairs of the sums in S star. Now what we do is we go over all the pairs in our R. So we're going to we have to check, so we get all these union of covers of all these pairs of sums. So we first take a look at R, the leftover one. That's the easy one. So we go over every pair in R, which is a point from A and a point from B. Now this point, and we compute their sums for all the pairs. So in other words, if we take a look at this element from A, what it really came from is initially it was rounded down. It was like a line going through it, because initially we had this line and then we rounded them down. So we have this line going through the square. So really it's an R by R point, but there's only R points of interest in the original A. And the same is true for B. So we take every single original point from each, and we brute force. We actually just add their sum, and we check whether it's in the real upper envelope. We check whether it's there or not. And then we go over all the pairs AI and BI for the rounded down ones. Now AI is a collection of these r by r squares, and each one, now we can't do what we did before, because initially we went over every pair, but here it's going to cost us too much. So what we do is we take this value, we just know who they originally came from. There's r squared original A points, and we denote AI to be all the original points of AI star. Not the ones that are really there or not really there, just that's what we call AI. And we do the same thing for BI. So we define BI for BI star. Okay, so they come from some set of original points. We define these 2 points. And now, since we know who AI and BI are, so we use this sparse FFT to compute AI plus BI. And once we've computed them, then we take all the we take a look at all the points in AI plus BI, and then we can check them whether they belong to S. And we'll show that there's not too many of them. And then once we've checked all these points, we've overcounted for these points, by the way. AI plus BI might be more points than we need, but that's fine with us. Then we check all these points, then we've checked everything, because these are all the sums that cover the rounded down version, so we might be overcounting, but it's okay. We're allowed to overcount. We're just checking too much. So each point in here, we have to check whether it really belongs to S or it doesn't. So what's the time for this? So rounding down is order of n time. That's not a big deal. Computing this, as we said, brute force is n divided by r squared. Using the BSG theorem, we do it in order O tilde of n divided by r squared time, because it's for the rounded down version, so we can compute the S star version. Now, we go over each of the pairs in R, but you have to know that R, according by the theorem, is beta of n squared, and beta, remember, our capital N is n divided by R, so we get beta times n over r squared, beta times n over r squared, but the number of pairs in R is, we said, is no more than r squared pairs, so we get r squared times beta times n divided by r squared, so that's beta times n squared. And here, we know that AI star plus BI star is at most is bounded by 1 over beta to the 5th n, which is 1 over beta to the 5th n divided by r. And then we go to compute AI plus BI. But as we said, the number of points for each one is at most r squared. So we multiply this by r squared, and we get r squared 1 over beta squared 5th n, which comes out to 1 over beta 5th n times r. And okay, so what you get here is you get n divided by r squared, and you get 1 over beta 5th n divided by r and beta of n squared. Putting all these together and sticking in the correct beta and r, and forget about the adding recursion to r, but you get a solution which is n to the 1.86 something. If you do a little bit tightening the screws by adding recursion, you can even come down a little bit further, and you get this one, n to the 1.859, which we mentioned. So that's the result. So let me just mention some other applications which fit into this framework. So this has been shown in several variants, but it follows directly from here. So truly, if you take integer 3 sum, if you can partition the sets into n to the 1 minus delta clusters, where each one is covered by intervals of length n, you can actually get a better result as well. And you can take also the histogram indexing, and you can solve it for any constant d, which closely matches a conditional lower bound of myself together with Yehuda Mir and Timothy Chan in a previous ICAL paper. And finally, the real question is how far can we actually extend these results, these algebraic results, and does algebra give us more than we're hoping for and showing lower bounds for that we're going to be doing in the next few days. So that's it. Thank you.
Any questions for Moshe?
Do you know if this exponent 5 is height in the BSG theorem?
So the question is a good question. It's been around for quite a while, so it's probably quite hard. But What you can really ask yourself is maybe for these applications, maybe you can get something better for the specific applications. Maybe you could do a little bit better.
Okay.
Thank you.